Black holes are one of the most fascinating and mysterious phenomena in the universe. They are regions of space where gravity is so strong that nothing, not even light, can escape. They are formed by the collapse of very massive stars or the accumulation of huge amounts of matter. They have a boundary called the event horizon, which marks the point of no return for anything that falls into them. Black holes are invisible to the naked eye, but they can be detected by their effects on the surrounding environment. For example, black holes can attract and devour nearby stars and gas, forming a disk of hot, glowing material around them. This disk can emit powerful jets of radiation and particles that can be observed by telescopes. Black holes can also distort the light from distant objects behind them, creating a phenomenon called gravitational lensing. There are different types of black holes, depending on their size and origin. The most common ones are stellar mass black holes, which have masses ranging from a few to dozens of times that of the Sun. They are the remnants of massive stars that explode as supernovas at the end of their lives. The first black hole ever discovered, Cygnus X1, belongs to this category. Another type of black holes are supermassive black holes, which have masses of millions or billions of times that of the Sun. They are found at the centers of most galaxies, including our own Milky Way. They are thought to have formed in the early stages of the universe, by the collapse of huge clouds of gas or by the merger of smaller black holes. They play a crucial role in the evolution of galaxies, as they influence the formation and growth of stars and planets. The largest black hole ever observed, M87, has a mass of 6.5 billion solar masses and a diameter of about 40 billion kilometers. A third type of black holes are intermediate mass black holes, which have masses between those of stellar mass and supermassive black holes. They are the most elusive and controversial ones, as their existence and origin are still uncertain. Some possible candidates have been detected by gravitational waves, which are ripples in spacetime caused by the collision of massive objects. The heaviest black hole ever detected by gravitational waves, GW 190,521, has a mass of 142 solar masses and is likely an intermediate mass black hole. Black holes are not only fascinating objects, but also powerful laboratories for testing the laws of physics. They challenge our understanding of gravity, space, time, and matter, and reveal the limits of our current theories. They also inspire our imagination and creativity, as they are often featured in science fiction and popular culture. One of the most intriguing aspects of black holes is what happens inside them. According to the general theory of relativity, the theory that describes gravity in spacetime, the matter that falls into a black hole becomes compressed to a point of infinite density and zero volume, called a singularity. At this point, the laws of physics break down and become unpredictable. However, the singularity is hidden from the outside by the event horizon, so we cannot observe or measure it directly. Another possibility is that the matter that falls into a black hole undergoes a process called quantum tunneling, which allows it to escape through another opening in spacetime, called a wormhole. This would create a connection between two distant regions of the universe, or even between different universes. This scenario is based on the quantum theory, the theory that describes the behavior of subatomic particles and forces. However, there is no experimental evidence or observation to support this idea. The challenge of reconciling the general theory of relativity and the quantum theory is one of the greatest unsolved problems in physics. Many physicists have attempted to develop a theory of quantum gravity, which would unify these two frameworks and explain the nature of black holes and singularities. One of the most promising candidates is the string theory, which proposes that the fundamental constituents of matter and energy are not point-like particles, but tiny vibrating strings. This theory also implies the existence of extra dimensions of space, beyond the three that we perceive. Another way to explore the mysteries of black holes is to simulate them using powerful computers and mathematical models. This approach can help us visualize and understand the complex phenomena that occur around and inside black holes, such as the formation of accretion disks, the emission of jets, the bending of light, and the production of gravitational waves. Some of the most realistic and detailed simulations of black holes have been created by the Event Horizon Telescope project, which is a global network of radio telescopes that work together to observe the supermassive black holes at the centers of galaxies. The EHT project made history in 2019, when it released the first ever image of a black hole's shadow, which is the silhouette of the event horizon against the bright background of the accretion disk. The image showed the supermassive black hole at the heart of the galaxy M87, which is 55 million light-years away from Earth. The image confirmed the predictions of the general theory of relativity and provided a new window into the extreme physics of black holes. One of the most exciting prospects of studying black holes is to discover new phenomena that we have not yet observed. For example, one of the predictions of the general theory of relativity is that black holes can spin, creating a region of spacetime around them that rotates with them. This region is called the ergosphere, and it can have strange and interesting effects on the objects and radiation that enter it. For instance, it can extract energy and angular momentum from the black hole, creating a mechanism known as the Penrose process. This process could explain the origin of some of the most energetic events in the universe, such as gamma-ray bursts and quasars. Another prediction of the general theory of relativity is that black holes can merge, creating a bigger and more massive black hole. This process releases a huge amount of energy in the form of gravitational waves, which are detected by instruments such as the Laser Interferometer Gravitational Wave Observatory and the Virgo Interferometer. These detections not only confirm the existence and properties of black holes, but also provide new information about their formation and evolution, as well as the history and structure of the universe. A third prediction of the general theory of relativity is that black holes can evaporate, losing mass and energy over time. This phenomenon is called Hawking radiation, and it is based on the quantum theory of fields in curved spacetime. According to this theory, black holes can emit particles and radiation due to the fluctuations of the vacuum near the event horizon. This implies that black holes are not completely black, but have a finite temperature and entropy. However, Hawking radiation is very weak and difficult to detect, especially for large and massive black holes. It is still an open question whether black holes can completely evaporate, and what happens to the information and matter that they contain. Black holes are the ultimate challenge for our scientific curiosity and exploration. They represent the frontier of our knowledge and the limit of our observation. They are the source of many questions and mysteries, but also of many discoveries and insights. They are the embodiment of the beauty and complexity of the universe, and the expression of the creativity and ingenuity of the human mind. They are the ultimate adventure and the ultimate mystery, and we are still learning more about them every day. Thank you for watching this video. I hope you enjoyed it and learned something new. If you did, please show your support by subscribing to this channel, leaving a comment, and giving a like.